Hello and welcome back to MV Tutors. I'm Telo and I'll be looking at chemistry with you. So without even wasting any time, let us get straight to it. Please don't forget to like our videos as well as subscribe to our channel. Alright, multiple question or multiple choice questions. So with 1.1, it says the functional group for an aldehyde is a... Okay, looking at the options here, A, is it the formal group? Yes, it is. Remember, with an aldehyde, the carbon at the end or at the beginning has a double bond to oxygen, right? And one bond to hydrogen and another bond to carbon and so forth. All right, so an aldehyde consists of a carbonyl as well as a hydrogen at the end. So that's why we refer to it as a formal group. A carboxyl group, that is for the carboxylic acid. A carbonyl group, that would be mainly for ketones or esters. Hydroxyl group will be for alcohols. All right, and then 1.2. Which one of the following equations represents the reaction for the identification of an unsaturated organic compound in the lab? Okay, so for A, actually, the first portion, I see that we have a double bond. So we have an alkene, all right, and then we add hydrogen there. So firstly, addition reaction, hydrogenation. Secondly, we have an addition reaction again, which is hydrohalogenation. Thirdly, again, we have an alkene, addition reaction with bromine, bromination or halogenation. And then finally, we have an alkane, but this time with bromine. So this is a substitution reaction. Okay, and then we have our results there. So D we can immediately take out, okay, because we're not substituting here. So if we have a look between A and C, A, B, and C, actually C will be the correct answer. I don't know if you know this process called bromination. You know, bromine is a brown colored compound, okay, and it would disappear if a hydrocarbon is unsaturated. So that is what we normally use in order to see if we have an unsaturated organic compound or not. Had it been saturated, like in the case of D, then the brown color wouldn't disappear. Okay, so the process of bromination here. So we're gonna go with C. 1.3. Which one of the following is the empirical formula of ethyl ethanoate? Okay, so ethyl, that presents or represents the alcohol portion, and it is when you have two carbons, ethyl ethanoate. So in between, we have an oxygen there for an ester, and ethanoate, that comes from the carboxylic acid. So you have the double bond to oxygen, and you have your hydrogens there. Okay, so this is your ester, right? Ethyl ethanoate. Now, since that's the case, what is the molecular formula? So molecular formula is what you have in total. So I see here I have 4 carbons. Our hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 hydrogens and 2 oxygens. So this is our molecular formula. Our empirical formula is when we simplify this molecular formula. Oh, sorry, 2. If we simplify this molecular formula, I can divide by 2 everywhere. And if I divide by 2, that's the common factor, basically. I'm left with 2 here. I'm left with 4 and 1. So this is our empirical formula. And which option do we choose there? Well, I hope you see that it is A. Okay. So far, not so bad. Let's hope the rest of the paper goes like this. So it says, in an experiment, 5 grams of calcium carbonate reacts with excess hydrochloric acid. Okay, they put excess there in capital letters. What does that mean? It means you have so much hydrochloric acid that our limiting reactant here will be calcium carbonate. Okay, so once calcium carbonate finishes, the reaction is complete. Now, the volume of carbon dioxide produced versus time is shown by curve P. The experiment is repeated with 10 grams of the same calcium carbonate. Okay, So now we have increased the amount, okay, of calcium carbonate. What does that tell us if we increase the amount? Okay, but let's continue reading. The experiment is repeated with 10 grams of the same calcium carbonate sample and an excess of hydrochloric acid with the same concentration at 40 degrees. Okay, so which one of the following curves will be obtained? So this is now where your rate of reaction comes in. The temperature is the same, all right, but now we have increased the amount of calcium carbonate. What effect does it have? Remember, we're looking now what influences the rate of reaction. That would be your surface area. Is there a catalyst, temperature, nature of reactants, concentration. So here, when we increase the amount of calcium carbonate, remember calcium carbonate is our limiting reactant. So if we increase the amount of calcium carbonate, we are also increasing the amount or the volume of increasing the volume of carbon dioxide gas. Okay, one thing. Okay, and if we've increased the volume, we're going to look at option 4 and option 3 on our diagram. But here's the thing: if you also increase let's look at concentration. Would concentration be increased? So concentration is number of moles over volume. Okay, and what happened? You increase the amount. Okay, remember, number of moles is mass over molar mass. Okay, so yeah, if you increase the mass, you ultimately increase the number of moles, and if you increase the number of moles, you're also increasing the concentration. If you're increasing concentration, you're also increasing the rate of the reaction. So we're expecting a steeper graph to P. Okay, so if it's steep, we're looking at option 2 and option 4. But if we're looking at the amount that increased, we're looking at option 3 and option 4. So the common denominator here is option 4. So our answer is D. Now 1.5. The balanced equation below represents a reaction at equilibrium. So we have chromate at hydronium, gives us dichromate and water. Okay, if we're looking at this formula over here, on the left-hand side, which one is the acid? Okay, so in this case, you need to check which one is the acid, which one is the base. Okay, because it then says which statements is or are true when a few drops of concentrated hydrochloric acid are added to the mixture. Okay, so it helps identify which one is the base, which one is the acid, because you are adding more of an acid. All right, and you're going to have to use Le Chatelier here a bit to sort of determine what happens ultimately. So hydronium, I know for a fact that it is an acid, and if this is the acid, let me just make this pen a bit less thick. So if this is the acid, this would be the base, and you know an acid has a tendency to donate. So this would be your base, and then that becomes your acid. So now, I'm adding a few drops of hydrochloric acid. I am increasing, okay, I'm increasing the amount of the acid. Now, if I increase the amount of the acid, I am then increasing the amount of the reactants. What does Le Chatelier say? If we have our seesaw there, I've increased the reactants, so now they weigh heavily. Le Chatelier says, okay, now in order to counteract that, in order to get back to a new equilibrium, I am going to have to increase the products. Okay, so now this reaction will be forward favored or product favored. All right, and in that case, if it's product favored, then what you're going to see is you're going to have a lot of your dichromate, so it will be more orange. Okay, so the orange will become darker. Oh, there'll be more orange. Let's just say that. So let's look at the options that we have. So the reverse reaction will be favored. No, we said it's going to be the forward reaction. The concentration of dichromate increases. Yes. Yeah, so the concentration of it increases, yes, so number 2 is true. The color of the solution changes from yellow to orange, yes, it does. Okay, so we're looking at option 2 and option 3, and that is D ultimately. Okay, so there we go. So D is our answer. What did I do now? Yeah, okay, and now 1.6. Consider the equation below for a hypothetical reaction. All right, so we have A in aqueous solution, B solid, C aqueous, D aqueous. If the equilibrium constant is that, then what happens? Okay, let us write down our equilibrium constant equation where we have the concentration of the products. So in this case, we have C, concentration of C, concentration of DO over concentration of A. Are we going to include B? No. If you have a concentration of a solid, okay, or a liquid, that will just be equal to 1. So we don't write it down. All right. So this is then our formula. And they tell us that our equilibrium constant is less than 1. 1 times 10 to the negative 4 is 0.0001. Okay, so this is less than 1. If it's less than 1, so we have a very, very low Kc value. It means our concentration of our reactants is actually higher than that of our products. Okay, it has to be higher for the Kc value to be low because the two are inversely proportional. Okay, so looking at the options here, A and B will not be included because B is not part of the equilibrium constant equation. So yeah, C, D, we're definitely going with C. Which one of the following shows the products for the reaction of oxalic acid with sodium hydroxide? Okay, so you have a weak acid. I don't know how oxalic acid, okay, I do know how it looks, but I'm just saying in the event that you don't know the formula for oxalic acid, just know that it is a weak acid. You know, it doesn't feature like your hydrochloric or sulfuric acid or phosphoric acid. Okay, so you have a weak acid and a strong base. Okay, any hydroxide is a strong base. If you had a carbonate, that would be a weak base. Okay, so you have a weak acid and a strong base. And then in this case, because this strong base is sodium hydroxide, your product will be a salt and water. If it was a weak base like a carbonate, then you would have carbon dioxide as a product. Okay, so if it says which one of the following shows the products for the reaction of oxalic acid with sodium hydroxide, by the way, oxalic acid is actually it's you have a carbon and a carbon, and then you have your Cu there on either side. So this is how it looks. Now actually drawing this incorrectly. Yeah, this is how oxalic acid looks, by the way. But anyway, option A and D are out because we see in the products we have carbon dioxide, which is not the case. Okay, so we can scratch that out. Now we can focus on B and C. Okay, I see here with oxalic acid I have 2 carbons and sodium hydroxide. Yeah, sodium hydroxide. Okay, this is oxalic acid plus sodium hydroxide. So for option B, I see I have 2 carbons, right? And then we have our sodium there and water. And option C, I have 2 carbons. Okay, that's fine. How many oxygens do I have? I'm just trying to gauge in the event that I don't know what the product should be. What am I going to go with in an exam situation? Okay. So if I look at the amount of oxygens, I have 1, 2, 3, 4, 5 there. So if I look at B, I have 1, 2, 3, 4, 5. C, I have 1, 2, 3. So I have fewer oxygens. So I'm inclined to go with B. This is like, flight or flee situations. Like, yeah, what am I sort of like expecting? But if you do know that oxalic acid that's exactly how it looks, then you would know this is your product, sorry, your reactants, okay? And your product, therefore, would be this, the first portion of it, because remember, sodium is positive, hydroxide is negative, and you have your Cu there, which has a negative charge, and OH there. No, H, which is positive. Okay, yeah. So this would bond with that would bond with that, hence you have H2O, and then you have, I would have written it this way. Rather, I would have said, put the sodium in front. I prefer putting the positive in front. Okay, and then water. All right, I would have put it like that, but because we have two of that, so we just need to put it there. Okay, that's, yeah, if you knew what oxalic acid is, but if you didn't, you just gotta, yeah, just we will take a spanzolanyan. Okay, 1.8, 4 solutions of different acids of the same concentration are compared. Which one of the following Ka values represents the weakest acid at 25 degrees Celsius? Okay, so I mean, if a Ka value that's weak, you're looking at a number that's the lowest. Okay, so I think here they give it to you straightforward. So if you look at A, I'm not even going to look at 4,5. I'm going to look at 10 to the power, that exponent. So minus 6 is really the lowest that I see here. We have minus 5, minus 2, minus 2. So A, I think it's obvious that it's going to be the answer there. 1.9. So copper is purified by electrolysis. Now, which one of the following combinations is correct for the changes occurring at the anode, cathode, and in the electrolyte when the cell is in operation? Before we even look at the answer, you know at the anode, that's where oxidation occurs. Okay, so the mass of the anode will decrease. Okay, it loses weight while the cathode gains weight. Now the answer, now the question would be, what then happens to the electrolyte in this case? Okay, so remember, we're just dealing with copper here. Okay, what happens on the one side? We have copper electrodes, by the way. Okay, what happens on the anode? Copper is reducing. At the cathode, copper is increasing. It's just copper. Okay, so in terms of the color of the electrolyte, we're not really expecting any change. Maybe if they use different electrodes, like maybe platinum, then yes, we would start to see the blue, is it blue color? Yeah, you'll start seeing it changing. Okay, so yeah, so basically the copper ions the copper ions in there will just pretty much have the same concentration, so the electrolyte will remain unchanged. Okay, so in this case, let's look at the options then. So we're saying the anode, the mass of the anode will decrease, so we're looking at option B and D. Mass of the cathode increases, yes, option B and D are still applicable. Color of the electrolyte, no change. Okay, so we're going to go with B then as our option. All right, 1.10. Which one of the following redox reactions is spontaneous under standard conditions? Okay, so what we need to then check is what happens at the anode and what happens at the cathode, and then use those numbers from the table, our table of standard reduction potentials, okay? And if it is spontaneous, then it would have a positive reduction potential. And if it's negative, then we know that it doesn't happen spontaneously. Okay, so for A, let's just have a look at what happens with bromine, because that one undergoes reduction and chlorine undergoes oxidation. Okay, I just want to write them down. So we have iron and we have iodine. Iron is the one that undergoes reduction. Nickel here undergoes reduction. And then you have hydrogen, which undergoes oxidation. Okay. Yeah, we have bromine there. Now I'm rewriting this thing. Okay, then we have copper, we have lead. So lead is the one that undergoes reduction, and copper undergoes oxidation. Okay, I think we're cool. Let's just go to the table and see what is actually happening here. Table 4b. So yeah, let's see from the top. So bromine, I know it's somewhere there at the bottom. So bromine is 1,07, and then chlorine there 1,36. Okay, this undergoes reduction, this undergoes oxidation, by the way. All right, and then we have iron 3 plus, we have 0,77, and then we have iron, so it is 0,54. All right, then we have nickel. Where is nickel? Nickel negative 0,27, and our hydrogen there, I think it's at 0. Yep. 0, and then copper. Okay, let's start with lead. Lead is negative 0,13, and copper is 0,34. Okay, so what are we going to do with these numbers? Remember the E cell, we start with the cathode. Cathode, that's where reduction occurs, minus the anode. Okay, so or reduction minus oxidation. So here with bromine, reduction 1,07 minus oxidation, well, we're going to get a negative there. And then reduction 0,77 minus 0,54, we get 0,23. So that's positive. So that happens spontaneously. And then you have nickel. Okay, that's negative, so that doesn't happen spontaneously. And then you have lead. Okay, so lead is, that's the reduction, that's the oxidation. Sorry, the way I wrote it. So you have negative 0,13 minus 0,34. Okay, so basically iron wins. Ooh, that was a long procedure, but ultimately B is the correct answer, and we're done with question 1. Question 2. All right, letters A to H in the table below represent 8 organic compounds. Okay, so what I normally do, I want to normally put the structural formula so that I see what happens. Okay, so for A, we have butane 2-ol. So but tells me I have 4 carbons, and on the second one, that's where my alcohol is, my OH group, my hydroxyl. Okay, and then for B, yeah, I'm just going to draw the straight chain there. So CH3, then I have my carbon, and on one side of the carbon, I actually have 2 methyl groups, and then I have 2 carbons there with their H's, and okay, so this carbon, the longest chain that I have, 1, 2, 3, 4, 5, and this is an alkane, so I have a pentane. Okay, so yeah, 2,2 dimethyl pentane, that's what I'll call it. And then C, what's happening there? 3-ethyl pent 1-ine. Okay, so I have again 5 carbons. And then on the third one, I have an ethyl group. So CH2, CH3, that's my ethyl group. And on the first carbon, I have a triple bond. Okay, so that's my 1 carbon there with 1 H. Okay, so that's C. And then D, CH3, CH2, C. Okay, so 1, 2, 3. How many CH2s? 1, 2, 3. So 1, 2, 3. Just have my normal hydrogens. And then I have C. it can't be an OH group, so I have a double bond to oxygen, and so this is an aldehyde. Okay, it's an aldehyde. 1, 2, 3, 4, 5. So pentanol. Okay, that's what I would name it. E. Which one is the longest chain? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the longest chain is 6 carbons. Né? Okay, CH3, CH2, CH, and a double bond to C, and then CH2, and then CH3. And then at that double bond, that C there after the double bond also has an ethyl group. Okay, so what would I name E? Do I start numbering here? 1, 2, 3, 4? Or do I go 1, 2, 3, 4? I prefer that. So on the third carbon, we actually have an ethyl group. Okay, so 3 ethyl, and then we have a double bond. So the longest chain, 1, 2, 3, 4, 5, 6, we have 6. So we have 3 ethyl hexene, but the double bond is on the third carbon, so hexene. Okay, and then what happens at F? Butane 1 all. Okay, we had butane 2 all, now it's butane 1 all. So there's the OH, no, OH group. Okay, and then almost there, G. Oh gosh. So the longest chain here, 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. Okay, so I have a CH3, then I have a C, then I have a CH2, then a CH, and then a CH, and then another CH, and another CH3. Okay. CH3. Okay, let's start again. So CH3, and on the second carbon, I have chlorine, and I have an methyl group. The third carbon, CH. The fourth carbon, I have a CH3, and just the H. And then the fifth carbon, I have a CH, and the Cl. Wait. Yeah, so CH3, C, CH2, confusing myself here. CH3, C, CH2, then a CH3, one, two, three, 4. Okay. Yeah. All right, so the fourth one, I have a CH3. The fifth one, I have a Cl. Ooh. And the CH, and then the last one, CH3. Okay, I've stopped confusing myself. So, where do I start? Do I start counting here? 1, 2, 3, 4, 5, 6? Or do I count the other way? 1, 2, 3. I think the more dramatic one is this side. Okay, if I start counting here, 1, 2, 3, no. So what would I name this compound? Okay, so looking at, I have chlorines and I have methyl groups. So the one that will come first is chlorine. So therefore, in that case, I will go for 2, 5 dichloro. Okay, and then also 2, 4 dimethyl. And this is the longest chain is hexane actually. This is a pentane. This is a alkane group. Okay. Ooh, G. Now H. Okay, if I draw that in a straight line, I have C, C, C. I have a double bond to oxygen and a hydrogen there. My second carbon, I have methyl groups. And my first carbon is just the normal. Okay, what would I name this? So I would say 2,2 dimethyl. Yeah, 2,2 dimethyl. This is actually an aldehyde. Yeah, so 3 carbons, so propanol. So 2,2 dimethyl propanol. There's no need to say propan 1L. Aldehydes are always at the end. Okay, so we're done. We're done looking at this in detail. Now we can answer questions. So define the term hydrocarbon. Well, that's basically a compound that consists of hydrogen and carbon atoms. 2, 1. Write down the letters for 2 compounds that are unsaturated hydrocarbons. So unsaturated hydrocarbons, E is one of them because we have a double bond there. What's happening now? Okay, and C, we have a triple bond at C. Okay, so C and E would then work. So C and E. So for me, it helps to see it like this because then I can actually see the double bond and also the triple bond there at C. Okay, and then 2.2.2, 2 compounds that are chain isomers of each other. Okay, I see positional isomers. Positional isomers A and F. But let's see. B, what do we have? We have how many carbons? We have 7 carbons. Is there anything else with 7 carbons? 1, 2, 3, 4, 5, 6, 7. So B and C have 7 carbons, but if I look at the molecular formula, because of this triple bond, it won't work out. I would have said this is a chain isomer because with the chain isomer, one is either branched, the other is a straight line, you know, something like that. So B and C would have worked nice, but because we have a triple bond, the molecular formulas are going to be different, and that defeats the whole purpose of it being an isomer. If I look at D, we have pentanol. There is no other aldehyde with 5 carbons. Nope. Then we have a G, which has how many carbons? It has 7 carbons. No, 8. No, 9. We have 6 carbons here. Yeah, 7, 8. So, geez, no. I think they meant to say positional isomers because I don't see any other isomer except for butane 2-ol and butane 1-ol. So I'm going to say A and F. 2,2,2, A and F. Okay, and then 2,2,3. A secondary alcohol. Okay, so it's going to be between A and F. So F, we can see is a primary alcohol, okay, because this carbon is only attached to one other carbon. A, we can see this carbon is attached to 2 other carbons. So that's going to be A. And then now 2.3. So it says write down the structural formula of the functional isomer of compound D. So compound D, this is what it was. Okay, we have pentanol. A structural formula for the functional isomer. So now we're going to go from aldehyde to ketone. Okay, so for it to be a ketone, you can either put a double bond there, or you can put a double bond there. I like it in the middle, so that's where I'm going to put it. And it's going to go from pentanol to pentone, right? Pent-3-one. Okay, but they wanted the structural formula, so I need to put in the hydrogens. Okay, we need to. Okay, let me see. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, if you wanted to provide the name, we could have said 1, 2, 3, 4, 5. So pentan 3. Oh, okay. So from aldehyde we got no ketone. From aldehyde to ketone. So pentan 3-one. Okay, that would be, but they didn't want the name. They just wanted a structural formula. Now 2,3,2. General formula of the homologous series to which compound B belongs. So remember, compound B is an alkane. So we are 2,2 dimethylpentane. And if you have a pentane or an alkane, you have CnH2n plus 2. All right, and you can go and count. You'll see that it supports this formula. And then 2,3,3. Write down the structural formula of compound C. Okay, structural formula. I will have to edit it a bit. But yeah, copy. Structural formula for compound C. I know in an exam you can't exactly copy and paste. Sorry. Okay, so let's just draw this proper. We have a triple bond. Then we have our hydrogen. And then here we're going to have to put the hydrogens properly. There's our CH3. So this is our ethyl group. I need to make sure there are 4 bonds around hydrogen, around carbon. So yeah, 2,3,3. That's basically the structural formula of compound C. Okay, which is 3-ethyl, pent 1-ine. And then now 2,4. Write down the IUPAC name of compound E. Okay, so we have E, we have G, and we have H. Okay, let's start with H. H, we said it is 2,2 dimethyl propanol. Copy and paste. Okay, there we go for H. And now G, let's go get it. Ooh, that long name. 2,5 dichloro, 2,4 dimethyl hexane. There we go. We have its name right there. And then E, we have it as 3-ethyl hex 3-ene. And we are done with that naming. Okay. You will see what works best for you in an exam. My method looks like it wastes a lot of time. But I prefer it this way. Now 2.5 says compound B undergoes complete combustion. Okay, where is compound B? I'm just going to copy it so that I don't always have to refer to it. Okay, compound B. All right, we have the name there. Oh, it was a condensed structural formula. So it undergoes complete combustion. Now using molecular formulae, write down the balanced equation for this reaction. So how many carbons do we have? 1, 2, 3, 4, 5, 6, 7. We're writing out the molecular formula. The hydrogen, since this is an alkane, hydrogens, I'm expecting them to be 16 because 7 times 2 is 14 plus 2, 16. Okay, remember we wrote down the formula. So if it undergoes combustion, then we have oxygen over there, and our compound that we are expecting is, I like starting with water. Actually, it doesn't matter. We have carbon dioxide and water as our products. So let's start balancing. I have 7 carbons. All right, so I'm going to put 7 over there. And then I have 16 hydrogens. Okay, so I'm going to put 8 over there. So it's balanced, but now the oxygens. Here I have 7 times 2, I have 14 oxygens plus 8, which is 22 oxygens. So this side I have 2, I'm going to multiply them by 11. Is that it? Yeah, that's it. Let me just erase this. And that's it for question 2. Question 3. All right, so it says the boiling points of some organic compounds are shown in the table below. The atmospheric pressure is 103.3 kilopascal. Okay, what's happening with A? So we have CH3. I like structural formulae, guys. It helps me see. I'm a visual learner, so I can see properly what's happening if I have it all in a straight line. Okay, and then, so I have CH3, 1, CH2, CH2, and then CH2Cl. So the last one, I have a chlorine and some hydrogens. Okay, so it's I have a haloalkane. Haloalkane. And then B, CH3, CH, so I have one H and then a branch there, and then CH2, Cl. Okay, I think it's also a haloalkane as well. So it's a straight haloalkane. And now I have a branched haloalkane. Okay, now C, again CH3, CH2, CH2, and then CH2, but I have a OH group, so this is an alcohol. And then D, I have a CH3, CH2, CH2, and then C, just HO, so there must be a double bond, and then H. Okay, let me just put it in. So this is an aldehyde. All right, and then the boiling points, guys. Okay, so obviously the alcohol in here has to be the highest in terms of boiling points. So I'm going to put here boiling point ranking. Which one is the highest? I'm expecting alcohol to be number 1 because, I mean, we have an OH group, so that's the strongest. Okay, then I would expect the aldehyde to come in next because I have a double bond to oxygen. But, and it's a very strong but, chlorine has a molecular formula of what? Chlorine, okay, there it is. Chlorine has a molecular formula of 35,5. Okay, 35,5. Whereas aldehyde, oxygen, has a molecular formula of 16. So unfortunately, between aldehyde and this, the haloalkane of this straight, okay. So between the aldehyde and these two haloalkanes, the straight one, because now that it's branched as well, that complicates things. So we can see here for 3 point, yeah. We can see here that A has 78 and B has 46, okay. So I would, because I expected the aldehyde to be number 2 in terms of ranking, that chlorine just messed things up. So I'm expecting this to be number 2. But now between B and D, because again, we still have the chlorine, I don't know which one will be the strongest. So yeah, let's just leave it there for now. We'll continue ranking. Now 3.1 says, define the term boiling point. So the boiling point is basically the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Okay? So temperature of a substance where the atmospheric pressure is basically equal to the vapor pressure. 3.2, which one of compounds A, B, and C is mainly in liquid phase at 100 degrees. Okay, so basically A and B are out because they reach boiling points before 100. So C would have to be the one, okay, which is our alcohol there. 3.3, explain the difference in boiling points of compounds A and B. Okay, so this mainly has to do with the surface area. So compound A is a straight chain. Which then has a higher surface area. Okay, and because it has a higher surface area, it has higher intermolecular forces, therefore higher boiling point. Now B, on the other hand, is a branched chain. Okay, some would say that it's spherical, okay, but it has a branch basically, and because of that it has a lower surface area, and compared to A it has lower intermolecular forces, therefore its boiling point would be less. Okay, how many marks? Yeah, 3 marks. I think this would be fine for 3 marks. And then 3.4, it says consider the boiling points below. So we have 75, 120, 126. 3.4.1, which one of these values represents X, the boiling point of compound D? Remember, compound D is the aldehyde. And we said number 1 is alcohol because of the OH group. Okay, hydrogen bonding. So we can't have 120 and 126. So the aldehyde has to be 75 degrees. Okay, so 75 degrees is the one. So getting back to our ranking there, if A is 78 and D is 76, so that will be number 3. Then this branched one, because of it being branched, it is the lowest in terms of boiling point. All right, and then now 3.4.2, fully explain the answer in question 3.4.1. Firstly, the OH group. Okay, so we have hydrogen bonding. Let me just rather say compound C is an alcohol. Therefore, we have hydrogen bonding, which is the strongest bonding that we have. Bonding, which has higher intermolecular forces and higher boiling point. Okay. And then, so it cannot be 120 and 126. Now, comparing D and A, okay, A is a haloalkane, and that halogen, so Cl, chlorine, has a very high molar mass. Okay, chlorine has a very high molar mass compared to D, our aldehyde. Okay, so overall, the molar mass is less. Okay, and because we have a high molecular mass, and also the polarity there is quite high. We also have a higher polarity. All right, we are expecting the intermolecular forces of a haloalkane to be higher, and therefore the boiling point to be higher versus that for the aldehyde, which has lower intermolecular forces and therefore will have slightly lower boiling point, but they're quite close, guys. We can see that for the haloalkane, they're 78 degrees, whereas our aldehyde is 75. So they're quite low. It's just that molar mass did the things. If it wasn't for chlorine and we just had hydrogens, then definitely D would be number 2. Okay, and then lastly, 3.5, the atmospheric pressure is now changed to 83. So we went from 101,3 to 83. Okay, so basically the atmospheric pressure decreased. How will the boiling points of these organic compounds be affected? Okay, so basically atmospheric pressure is actually directly proportional to boiling point. So if it decreases, then the boiling point will decrease because the pressure is not so much anymore. You don't need to have higher intermolecular forces to overcome these bonds and have it, reach boiling point. So the boiling points will actually also decrease because of the atmospheric pressure decreasing. And that's it for question 3. Question 4. This is the question in the middle since chemistry has 9 questions now. All right, so question 4. In an experiment, a test tube containing methanol, I'm going to write there methanol, propanoic acid. Okay, so we have 3 carbons, propanoic acid. We have our Q there. And a catalyst. So we have a catalyst over there. Is heated in a water bath. Okay. I see I have an alcohol. I have a carboxylic acid. Okay, if I actually put this here, rather. Then we're going to have an ester, ultimately. Okay, and you know with an ester, we're going to take out the water. We're going to be left with the oxygen there in the middle, and we have a double bond, and then we have that situation over there. Okay, so on our side, we have methyl, because we have 1 carbon, methyl propanoate. That is the name of our ester, methyl propanoate. Oh, we also have that H2O that we took out. Okay, so this is our ester. Nice. Okay, let's look at the question. The catalyst. So, yeah, our catalyst here would be sulfuric acid. Okay, but anyway, let's look at the question. 4.1.1, write down the name or formula of the catalyst. Okay, this is sulfuric acid. Concentrated sulfuric acid, actually. And then 4.1.2, the type of reaction taking place. Well, an ester was formed, so we can say esterification. If you want to be fancy, you could have said it's an acid catalyzed because of the hydrochloric. Because of the what do you call this? The propanoic acid. So acid catalyzed, carboxylic acid, yes. Acid catalyzed condensation. Okay, but I like esterification. It's easy to remember because an ester was produced. Now 4.1.3, 2 reasons. Write down 2 reasons why the use of a water bath is preferred in this experiment. Okay, so this water bath, I think it's there to maintain temperature because in order to form an ester, this reaction is quite sensitive to temperature. So water bath can maintain temperature, but also it's also to ensure, because we're dealing with alcohol, that it was not flammable. So maintain temperature and reduce the flammability, if that's a word. Reduce the flammability because an alcohol is highly flammable. Okay, so yeah, but then again, also with the water bath, you want to prevent evaporation as well. Hence, you're maintaining the temperature because this is we want condensation here. We don't want evaporation. And also, it actually regulates the rate of reaction. Okay, regulates the rate of reaction or reaction rate. And what we want here, we want a high reaction rate. So yeah, the water bath will do the things that you need to do in order to form an ester. Okay, 4.1.4, write down the balanced equation for this reaction using structural formulae. We have actually done that. Balanced equation, so we're going to say, we're going to actually just copy and paste. Like, why must we do this to ourselves. Actually, no, I'm not going to copy and paste this. Let me write it out nicely. So we have our methanol. Ooh, I'm forgetting myself. Structural formula. Okay, so we have O has double bonds. So methanol plus propanoic acid. I'm going to try to squeeze that in. O. Okay, now I'm not fitting things in. O, H. Okay, let's put in the H's. 4 bonds around carbon, and then with the help of sulfuric acid, we now have 1, 2, 1, 2, 3. Okay, I have forced things here, and things are not going to fit in quite well, but here we are. We made it fit. Where there's a will, there's a way. Okay, we made it fit. Oh, snap, and there's that hydrogen. There's that water. So we have... Okay, no, we couldn't make everything fit, so plus H2O. We tried. Now 4.1.5. The IUPAC name of the organic compound for this reaction, we already spoke about it, so that is methyl propanoate. Okay, there we go. Methyl propanoate. And that's it for... No, we're not done. Oh my gosh. How can we be done? We're done with 4.1. 4.2. I was happy that we're done, but we're not. Compound A, a 6-carbon branched haloalkane, is used in a 2-step reaction to prepare compound C. Reaction 2 is an addition reaction. So we have compound A. I almost put a straight chain until I saw compound C. So compound A, we have our carbon over there, CH3. I'm not going to branch it out. Ooh, it's going to take forever. So it's a haloalkane. So we have single bonds. And we don't know where that halogen is at the moment. Okay, so this is A. Then it undergoes a reaction, 1. And then we have compound B. I believe the structure will still remain the same. So we're not going to change it. Okay, we have carbon. What happens with compound B, we don't know, but so this is reaction 1. But we know that reaction 2 is an addition reaction. Okay, if we have a haloalkane and then it undergoes reaction 1, I think, because for you to have an addition, you must have a double bond somewhere. Okay, I think here we're going to, I think reaction 1 has to be an elimination reaction. Elimination reaction. So that we have a double bond. And in order for us, for elimination, we're going to use Zaytev's rule. Zaytev says that with elimination, we're going to look at the carbon with the least hydrogens. Okay, and that's where we see where we can have a double bond. So the least amount of hydrogens is for carbon number, if I take that as 1 and that's 2, 3. Okay, so carbon number 3 has the least hydrogen, so I'm going to put the double bond there. And if I put the double bond there, okay, let me put it back there. So this is what we have. Okay, and we've eliminated something. I don't know what we have eliminated, but yeah, the double bond will go there because of Zaytev's rule, or Zaytev's rule. Then we have an addition reaction, and then ultimately, this is now B. Ultimately, we get to C, okay? And then C is just an alkane. We can see that, a branched alkane. CH3, CH3. We have a C. I'm going to put those CH2, and we have a CH3. What is that compound? So 1, 2, 3, 4. We have a butane. So we have 2,2 dimethyl. Dimethyl butane. Okay, so because I have all these hydrogens now, an addition reaction here, I think we got rid, for the elimination, we had to have taken out a hydrogen and a halide, okay, a halogen there, so that we just have a hydrocarbon, okay. So yeah, we have an alkene there, okay. What alkene is it? I'm not going to bother with the names for now, but that's compound B, okay. So this elimination, we took out HX, so it's a halogenation. No, dehydrohalogenation. We've taken away dehydrohalogenation. Okay, and then now an addition reaction. If we had an alkene, we are adding hydrogens here. Okay, so this is hydrogenation. All right, so that's reaction number 2. We have, yeah, I think we have everything. We can start answering questions. Write down the name or formula of the inorganic reactant in reaction 2. Okay, so what did we add there for reaction 2? We added hydrogen, okay, because we have hydrogenation. And then, now they're asking about the IUPAC name for compound B. Oh, very, so now we have to, we have to write it. There's no moving away from it. So because we have a double bond, we're going to start numbering here. 1, 2, 3, 4. Okay, so in that case, then we have 3, 3 dimethyl. I should have named it. So 3, 3 dimethyl, and we have a butene, right? Because we have 4 carbons, and on the first one, we have the double bond. So but 1 ene. Okay, and then 4.2.3. The type of reaction represented by reaction 1, that's an elimination reaction, but I'm going to go with dehydrohalogenation. Okay. Oh, you could have said elimination reaction just to be safe. Elimination. All right. Now, compound B is now used in a two-step reaction to prepare compound A. Reaction 4 is a substitution reaction. So compound B, there we are. I'm going to copy and paste. Okay. So we have compound B. We're starting with it. And we already said compound B is what? We said compound B is 3, 3 dimethyl but 1 ene, right? Okay, that's compound B. And then we have reaction number 3. Okay, and what happens afterwards? Then we have compound D. So I still think we maintain this shape. So CH3, the branches remain intact, and then CH4, and then C. Okay, I don't know what actually happens with compound D, so I'm just going to leave it there. Okay, and then we have reaction 4. What did they say about reaction 4? They said it is a substitution reaction. Okay, if it's a substitution reaction, I think we have gotten rid. Okay, no, before we even conclude, what is reaction for compound A? So compound A, we are back to the haloalkane. Okay. We are back to the haloalkane. Copy. And we have substitution. So what that tells me is we have single bonds for compound D. This is D. And because we have a compound B is an alkene, we have hydrogens everywhere. Okay, so I think from alkene, we have an addition reaction for reaction number 3. And this addition reaction, we're gonna, I think it's hydrogenation. Because at the end, we have a haloalkane. So now we just have a normal alkane. So D is an alkane. Okay, so we have, yeah. What alkane is it? Well, didn't we have an alkane somewhere? Yeah, it's 2,2-dimethyl butane. Actually, it's the same as C of the previous one. Okay, so yes, 2,2-dimethyl butane. And then it undergoes substitution. All right. So I think the halogen must be there. Okay. Because this is the carbon where, yeah, things are happening. I wouldn't put it on the first carbon, honestly. Well, in this case, this is now 1, 2, 3. No. Let's just leave it there. And let's answer the questions. Okay, 4.2.4. Write down the name or formula of the catalyst used in reaction number 3. So this addition reaction, hydrogenation. Okay, I'm glad we also chose hydrogenation, because if we said we're adding a halogenation, that doesn't have a catalyst. So with hydrogenation, a catalyst that you can use there actually is platinum. Okay, you can also use nickel or palladium. Yeah, but I think I would remember platinum. Now the IUPAC name for compound D. Okay, so the IUPAC name for compound D, that is basically, we wrote it down here, 2,2-dimethyl butane. Okay. And then 4,2,6. The type of reaction represented by reaction 3, well, we're going to say it's an addition reaction, which is hydrogenation. So, can put it right there. Okay, so this is going by quite fast, and then we are officially going to be done after answering this question. The type of haloalkane represented by compound A. Okay, choose from primary, secondary, or tertiary. So if we put our haloalkane there, a halogen. If we put our halogen there, you can see this carbon is attached to 2 other carbons. So it's going to be a secondary haloalkane. And that is it with question 4. Don't forget to like our videos and also subscribe to our channel. Question 5. The reaction between aluminium and excess sulfuric acid is used to investigate factors affecting rates of reactions. Okay, so there we have the balanced formula. Now, investigation 1. So, the effect of a catalyst on the rate of reaction is determined. Let me just summarize what we have there. So, we have aluminium powder. Okay, we know that if it's in powder form, the surface area is increased, right? Has a mass of 5 grams. it reacts with 0,1 concentration of sulfuric acid at a temperature of 60 degrees Celsius. Okay, now consider the following energy diagrams not drawn to scale for this investigation. X and Y in diagram B represent the activation energies. That's the Maxwell-Boltzmann diagram. So 5.1.1 is the reaction between aluminium and dilute sulfuric acid endothermic or exothermic? Give a reason for the answer by referring to the above diagrams. All right, so we can see that the products have a less energy than the reactants, okay? I normally look at this big space that we have after the products are formed. So energy has been released, so I would say this is exothermic. Sorry, this is what I mean by the big space. It's quite large. If it's on the right hand side, then it's exothermic. If it's on the left hand side, then it's endothermic. All right, so 5.1.2. What? Oh, give a reason. Okay, sorry. Exothermic, give a reason for your answer. Well, the energy of the reactants. Okay, energy of reactants, which is what? The energy of the reactants, that'll be the 240,8 minus 208,2. But anyway, the energy of the reactants ultimately, which is 208,2, okay, is actually larger than the energy of the products, which is 86,5 kilojoules. Okay, that's why it's exothermic. 5.1.2, what does the shaded area to the right of line P represent? So this one, it represents the number of particles that have energy that is higher than the activation energy. That's basically that. And then 5.1.3, determine the numerical value represented by the letter X on diagram B. So now remember, now for diagram B, we're dealing with kinetic energy. Diagram A, we're dealing with potential energy. Letter X has to do with the activation energy before the catalyst. Okay. So diagram A, it shows the effect of having a catalyst. Okay, and I'm going to show you right now. So basically, this is the effect of having a catalyst. Your activation energy, this was before, okay, now has been reduced. So you needed that amount of energy, but now because of a catalyst, the activation energy has reduced, and we can see it here. We can see it on diagram B that initially with X you needed a high activation energy, but as soon as there's a catalyst, your activation energy did reduce. Okay, so now here you have potential energy. So be careful not to just say that X is 240. 240,8, no, that 240,8 is the potential energy. Now what would be the kinetic energy? Okay, let's do a proper calculation. So if I take this back, okay, so X, we're gonna deal with that 240,8. Okay, so the change in potential energy will give us the kinetic energy. So 240,8 minus the energy of the reactants, which is 208,2, and that will give us the kinetic energy. So we have 240,8 minus 208,2, and that gives us kinetic energy of 32,6 kilojoules. Okay. And if you wanted the one for Y, you would have said 217,3 minus 208,2. All right. Now investigation number 2. Just remove this. Okay. Investigation number 2. The investigation is now repeated at 30 degrees using the same reactants. Okay. So basically, this is the same information. It's just now the temperature has reduced. So what does that do? Well, if the temperature has been reduced, the rate of reaction will also reduce. So now we have 30 degrees Celsius. All right, 5,2,1. How will this affect each of the following when compared to the investigation? So we must choose from increase, decrease, or remains the same. So the size of the shaded area in diagram B. Okay, so if this was your Boltzmann diagram, and that's, P, what's going to happen when you increase or decrease the temperature? Well, okay, it's going to go like this. And this now will be your shaded area, which definitely decreases. Now, getting back to the question, 5.2.1, the size of the shaded area, well, it decreases. So now you have less particles that have an energy that is higher than the activation energy. And then 5.2.2, the value of y, that remains the same. It doesn't change, okay? Remains the same. Okay, activation energy still the same. The only thing that changed is the number of particles that have an activation energy, that have an energy higher than the activation energy. Now 5.2.3, the total volume of hydrogen gas produced. So what would happen to the total volume of hydrogen gas produced? Well, even that one, it will still be the same because, okay, let's see, concentration, number of moles over volume. We didn't change the concentration, it remained the same. Also, the number of moles didn't change. It's just, yeah, because now we have less particles in there. Which affects the number of moles, because number of moles is the mass over the molar mass. No, actually, no, that didn't change as well, because your mass remains the same. Molar mass remains the same. So this remains the same. Volume also of gas produced remains the same. Okay. When you're in doubt, use a calculation or something. Use a formula. Okay. Now investigation 3. In this investigation, 5 grams of the same sample of impure aluminium powder reacts with excess diluted sulfuric acid at 60 degrees in each of the 3 runs. Okay, so we still have now similar conditions. Okay, still have the same 5 grams. Temperature is also still the same. Now what happens to the concentration? Okay, this is now 5.3. So what they're doing, the table below summarizes the conditions and the results obtained. Assume that the impurities do not react. Okay, still have the same formula there, but now we are varying the concentration. Okay, so concentration varies. Okay, temperature is still the same. Now 5.3.1, Write down the independent variable for this investigation. Remember, independent is on the x-axis, dependent is on the y. What are we changing and what is dependent on what? Okay, the independent variable, which is the x-axis, that would be concentrated concentrated sulfuric acid. No, why am I saying concentrated? Diluted. My goodness. Okay. So yeah, this is the concentration. So it's diluted sulfuric acid. That is our independent variable. And I say that because when we vary the concentration of sulfuric acid, then the rate, average rate of volume produced will go accordingly. And we see that once we increase the concentration, the average rate of volume produced also increases. Okay, but anyway, this is the independent variable. 5.3.2, use the collision theory to explain how the average rate of the reaction is affected in this reaction. Okay, what we are seeing here is when we increase our concentration, the reaction rate also increases. And why is that? So an increase in concentration, remember concentration, number of moles over volume. So we are increasing the number of particles, okay, in a particular space. Okay, so we have increased the number of particles, okay, in a particular space. Okay, it occupies a certain space. So the number of particles that are in a particular space region have increased. And if they increase, it means now we have better collision. Okay, so the likelihood of good effective collision will increase. Okay, so I'm going to say effective collisions that occur will increase. And if that's the case, then the rate of reaction also increases ultimately. And then now 5.3.3, the time for the reaction to reach completion in run 3 is 2.6 minutes. Calculate the percentage purity of the aluminium. Take the molar gas volume at 60 degrees to be 27,000 cubic centimeters per mole. Whew, okay. So we can then say the rate of reaction, okay, is basically equal to the change in our volume over the change in time, because that's what they've given us. The rate of reaction for run 3 is actually 40 cubic centimeters per second. And our change in V, which is our V final minus V initial, is, okay, we don't know what it is. Yeah, we don't know. We have the time, which is 2.6 minutes. And we're going to convert that to seconds. Okay, so then our volume, because the volume initially that was produced will be 0. So now I'm just going to say volume, I'm not going to say final volume. So now we have 40 times 2.6 times 60. So 40 times 2.6 times 60, that gives us 6,240 cubic centimeters. I like working with cubic decimeters, so it'll be divided by 1,000. It's going to be 6.24 cubic decimeters. That's our volume. All right, what are we doing here exactly? because yeah, you can calculate and forget what you're trying to do. You want to get the percentage purity. Okay, so your percentage purity will actually be the actual mass of your aluminium over the total mass, okay, which in this case of the impure is 5 grams. So we're trying to get the actual mass of aluminium here, the pure. We're trying to get the pure mass of aluminium. So if we have volume, and if we look at our equation here for molar mass, not molar mass, but yeah, that's the equation that we're going to use. Okay, molar gas volume formula. If we have our volume and they've given us our molar mass, molar gas volume, we can get number of moles. And from the number of moles, we can then get our mass, okay, which is number of moles times molar mass. So this is where we are working towards. This is the pure mass that we're trying to calculate. Okay. Yeah, now that we have the vision in check, what is the volume? We have 6,24 cubic decimeters, and our molar gas volume, that 27,000 cubic centimeters per mole, we're going to divide by 1,000 and we're going to have 27. So 6,24, actually we could have left it. 6,240 divided by 27,000. Okay, so we're going to get 0,23 mole. So all of this we were calculating for hydrogen. Okay, because this was for the hydrogen gas that was produced. Now we need to go and check in terms of the ratios. So we need for aluminium, let's start with the hydrogen actually. So for hydrogen gas, we have, according to the formula there, the balanced equation, we have 3 mole of hydrogen gas. And then for the aluminium that we ultimately need, we have 2 mole. Okay, and we have calculated then 0,23 mole for hydrogen. So how are we then going to get the number of mole for aluminium? Okay, so this is now where we say in order for us to get the number of mole for aluminium, we're going to take that 2 and divide it by 3. So we're basically working it out in terms of ratios. Okay, so 2/3 times that 0,23 will give us the number of mole for aluminium. Okay, so basically if we go 6,24 divided by 27, we get that 0,23, right? And we're going to multiply that by 2/3, and then we get number of mole as 0,15. So now ultimately we can get the mass of aluminium, okay, which is number of mole times molar mass. So then we have 0,15 multiplied by the molar mass. Let's check on the periodic table what the molar mass for aluminium is. And we find that, I don't know if you see here, the second block from your from your right, aluminium just under boron is 27. Okay, so we can go back and finish this calculation. So we have that multiplied by 27 and we get 4,16 grams. Now we can calculate the percent purity, which is what they wanted, of aluminium. So the actual mass, which is 4,16, multiplied by the impure mass, which is 5 grams, and we're going to divide it by 5 grams, and then we're going to multiply by 100 because we want a percentage. So 4,16 divided by 5 multiplied by 100 gives us 83,2%. So that's the percentage purity. And with that, we're done with question 5. Question 6. All right, so it says, consider the balanced equation for a hypothetical reaction that takes place in a 2 cubic decimeter sealed containers. Okay, so just note the volume there. We have 2 cubic decimeters. All right, so we have P2Q gas form, and then 3Q solid form, and then our product 2PQ2 as a gas. The graphs below, not drawn to scale, are obtained for the same reaction at 2 different temperatures. So we can see graph A is obtained at 298 Kelvin and graph B at 398 Kelvin. And we can see that equilibrium, so we have concentration versus time. So for graph A, equilibrium was reached at 0,4. And then when you increase the temperature, so when you increase the temperature, you get a less, so equilibrium is reached at a less concentration. Okay, so basically what that tells me then is that the forward reaction is not in favor of an increase in temperature. The reverse reaction is in favor of the increased temperature. So that means that is endothermic, and forward reaction is exothermic. Okay, because of the concentration that we see there for graph B being less. Anyway, 6.1, it says state Le Chatelier's principle. All right, so basically Le Chatelier's principle says that if your equilibrium or your dynamic equilibrium is disturbed, what we're trying to do, we're trying to get, or rather the position of the equilibrium will shift, okay, in order for it to counteract that disturbance. So there was a disturbance to the dynamic equilibrium. Le Chatelier says, okay, let's try to fix this. So the position of the equilibrium shifts and it counteracts the disturbance in order to re-establish equilibrium. Okay, like we see here for graph B, at 3 seconds to 8 seconds, or just before 8 seconds, there was equilibrium, then something happened, and then a new equilibrium was reached later on. So that's Le Chatelier. Okay, now 6.2, what do the parallel lines after t is equal to 5 minutes in graph A represent? Okay, so basically that tells us that we have reached, or the system has reached. Okay, so I'm not alone, so don't be surprised by this background noise. So the system has reached dynamic equilibrium. Miguel is snoring. Okay, system has reached dynamic equilibrium. All right, and then 6.3. Is the forward reaction exothermic or endothermic? Okay, so here it comes again. The forward reaction, we discussed it briefly. It's actually exothermic. Okay, and then we have to explain why that is. All right, so we see that with an increase in temperature, the concentration decreased for the forward reaction. All right, so if it decreases for the forward reaction, it means that the reverse reaction is actually favored. Okay, the reverse reaction is favored because we see that there the concentration is actually higher. Okay, and in that case, if the reverse reaction is favored due to the increase in temperature, it means that the reverse reaction is actually endothermic. All right, meaning that the forward reaction is exothermic. Okay, sorry guys. 6.5. Okay, how does the value of the equilibrium constant for the reaction in graph B compare to that in graph A? Okay, so is it greater than, less than, or equal to? Okay, remember that concentration, what is this? The equilibrium constant is actually affected only by temperature. Okay, so if you were to write down your equation, you know that that's the concentration of products divided by concentration of reactants, and we saw that our reactants are actually higher than our products. And if your denominator here is going to be high, it means your Kc value will be lower. Okay, so therefore the answer then would be less than. Okay, and then 6.6. Ooh, 8 marks. We know we're gonna draw the rice table. Actually, yeah, there's one thing that I wanted to comment on as I was looking at these graphs. It's just I forgot about it, but yeah, it's important for us to just look at it again and just discuss it. So for graph A, we can see that our products, we normally know that our products start at 0, right? So we can see this is our product. So that's PQ2, okay? Starts from 0 and over time it increases. Our reactant starts at a certain value and they decrease as the product is formed. Now for graph B, they have written, so this is again the product, okay, but I think they've made a mistake here. So this should be PQ2. Okay, let me just use a different colored pen with a smaller font or smaller thickness. Okay, so the product should actually be PQ2, and here would be our reactant over there, which decreases with time. That would be P2Q. And if you're wondering what happened to Q, well, that's a solid. We don't really consider that. Okay, especially when it comes to our Kc calculations. So yeah, consider the solid line to be your product, which is PQ2, and the dotted line to be your reactant, which is P2Q. Okay, I forgot to actually just state that. I'm sure you must be wondering what's happening. Okay, now when it comes to the equilibrium constant, they tell us that Kc is equal to 0.49. All right, it's less than 1, which tells us that our reactants are higher than our products. Now it says calculate the initial number of moles for P2Q. That is basically our reactant. Okay, so P2Q, the initial number of moles. So in initial, what is that? So we're going to have to draw our table there. Okay. So yeah, we're going to start with the ratio. I call it the rice table. Okay, so ratio and then initial amount of moles and then the change in moles and then our equilibrium. So this one will be mole per cubic decimeters. That will be mole. Everything else will be mole. I'm just so used to using mole. Oh my gosh, this girl. Baby girl, why are you snoring so much? Embarrassing me here. Okay. Yeah. So that's the ratio. And now we're going to look at our reactants. So we have P. Okay, P2Q. Okay, which is a gas. All right, and then we have 3Q. I actually shouldn't even be putting that in because it's a solid. It doesn't really play a part of this, but let's just put it in. just to show we have our reactants there. And then our product, we normally distinguish between the reactants and the products by using a double line. And then now we have our products, which is PQ2. Okay, and then ratios. So we have 1, we have 3, and we have 2. Actually, we're going to leave this out. Doesn't play a factor in anything. Initial number of moles. Well, we know that our product started off as 0. Our initial number of moles is what we're looking for. So I'm just going to call that X. And then what do we know? Looking at graph B, at equilibrium, we have 0.35. So I'm going to put that as 0.35. And then if I want to get the number of moles, remember concentration is number of moles over volume. Therefore, number of moles is concentration times volume. So our concentration is 0.35. Our volume, remember we noted it as 2 cubic decimeters at the beginning, right? There. So we're going to have 0.7 moles at equilibrium. Okay, and because we know that when we get to the change, the reactants decrease while the products increase. Okay, now if our equilibrium is 0.7, it means that the change then was 0.7. And we're going to use this and our ratios to get to the change for our reactant. So 0.7, we have 2 moles for our products versus 1 mole for our reactant. So we're going to divide by 2, and we're going to get 0.35 for our change. Okay, so now in terms of our number of moles at equilibrium, it's going to be X minus 0.35. And if we want it in terms of concentration, it's going to be X minus 0.35. Remember, we're looking for concentration, number of moles divided by volume. Okay, so once we have that, I think we can then use our Kc formula. So our Kc formula is the concentration of products, which is PQ2. Let me just switch this on so that we see PQ2, and that would be squared divided by P2Q. Okay, and remember we don't include Q because its concentration will just be 1. All right, and that's to the power 1. Okay, and that value is going to be equal to 0.49. So I'm looking then for the concentration of the reactants, which is concentration of P2Q. If I take it to the other side, I'm going to have to take 0.49 to the other side. Okay, I hope you got that. That's just some maths there. So we have that over 0.49. And what is our concentration for products? That's 0.35 squared divided by 0.49. And if we work that out, so we have 0.35 squared, okay, divided by 0.49. And that is equal to 0.25. And what is the concentration of our reactants? That's basically X minus 0.35 divided by 2. So now we have X minus 0.35. So 2 times 0.25, that's just 0.5. And 0.5 plus 0.35, that's just going to be 0.85 mole. That's the initial amount that we've been looking for. Okay, and that is your 8 marks. Now 6.7. Describe the change made to the equilibrium system at t is equal to 8 minutes, as shown in graph B at a constant temperature. So yes, the temperature has been kept constant there. It's still 398 Kelvin. But at 8 minutes, there is a, let me just switch that off. There is a decrease in both the reactants and the products. If it was just the reactants, we would have just said it's just a change in concentration. But now there's a change, a drastic change for both the for both the products as well as the reactants. So that tells us that there has been a change then, if it's both of them, change in pressure. Okay, you can have a look at our video for equilibrium and the different changes that come to our graphs when you increase or decrease temperature, pressure, concentration, addition of reaction, when you add a catalyst and so forth. So I discussed that at length. Okay, so yes, we have a change in pressure there. Okay, but what happened? Because now our concentration has reduced. 6.8, that's where we're trying to explain what happened in 6.7, because it says explain by using Le Chatelier's principle how the system reacts to the change in question 6.7. We see that there has been a change in concentration. They both reduce for the products as well as the reactants. Okay, so the concentration has decreased. If the concentration has decreased, it means there's been an increase in volume because the two are inversely proportional. Okay, and we know that if there's an increase in volume, there is a decrease in pressure. Okay, so ultimately, that change in pressure, it means that the pressure has been reduced. Now, what happens if the pressure has been reduced? We're going to look at, in terms of our reactants and in terms of our products, which one has the highest number of moles, okay? Because a decrease in pressure is going to favor the side that has the most amount of moles. So for the reactants, we only have 1 mole. For the products, we have 2 moles, okay, that are gaseous. Remember, pressure only applies to gas. So we have 2 moles. So the products are actually favored. So in decreasing our pressure, okay, forward reaction is actually favored. Forward. Okay, did I just, yeah, forward. So the forward reaction is favored. Okay, to say the products are favored. Okay, and if the forward reaction is favored, yeah, that's pretty much that. Decrease in temperature, no, a decrease in pressure due to that increase in volume has resulted in it being product favored, or forward reaction is favored. Okay, so this is how the system reacts to that change in temperature. And I hope that is clear and good. And that's it for question 6. Question 7. We're moving quite quickly. So a standard solution is prepared by dissolving 10 grams of sodium carbonate. I'm just going to say mass is 10 grams of sodium carbonate. So thinking that has to be like that. Yes. Okay, in that volume of water. Okay, so our volume is 0.7 cubic decimeters of water. All right. Now 7.1.1, calculate the concentration of the solution. So we know concentration is number of moles over volume. Okay, we have mass there. There's also another equation we can use, which is mass over molar mass times volume. So the mass that we have is 10 grams. The molar mass, okay, we're going to have to calculate there. Sodium carbonate, okay, we're going to need the periodic table. So let's just go there. Okay, we have 2 times the sodium. Sorry, please just bear with me as it looks like this. So the molar mass, we have 2 times sodium, 1 carbon, and 3 times the oxygen. All right, so then sodium is 23, and then carbon is 12, and then 3 times the oxygen, which is 16. Okay, so then what we're going to do, 2 times 23 plus 12 plus 3 times 16, 3 times 16, so there we get 106, okay, grams per mole. All right, so that's 106, and then what's the volume? Let's just go back. It's 0.7. Okay, so now we can get the concentration, which is 10 over 106 times 0.7. All right, so we get 0, 0.135. Just say 0.13. Okay, moles per cubic decimeters. Okay, remember this is grams, and that's grams per mole, so the grams cancel out, and that is cubic decimeters. So yeah, we're good. Okay, and now we get to 7.1.2. Let's just go back. Okay, 7.1.2. Will the pH of the solution be greater than or less than? So it's only 1 mark. So let's just think about it. You have sodium carbonate. That is a weak base. Okay? And I mean, it's in water. Water is neither here nor there. So in this case, this pH solution will be basic. Okay? Therefore, it will be greater than 7. Okay, and then 7.1.3, write an equation that explains the answer to question 7.1.2. So basically you have your, sodium in this case acts like a spectator. So you have your carbonate, which is the base, right? Carbonate has a charge of 2 minus, this is your base. And it's in water. Water will act as an acid in this case, all right? Okay, and then what happens then, because your acid tends to donate a proton, so you're going to have HCO3. Because you've added 1 proton, you're going to have minus instead of 2 minus. And then what are you left with? You're left with the OH there. So this just tells you that really we have a base here. So the pH should be greater than 7. Okay, 7.1.4. The sodium carbonate solution is titrated with dilute hydrochloric acid. Okay, the following indicators are available for this titration. So, sodium carbonate solution. All right, so again, we have a weak base, but it's titrated with a strong acid, because hydrochloric acid is a strong acid. Okay, so at the end, you're expecting your solution or your product to be acidic still. Okay, 7.1.4 says, which one of the indicators P, Q, or R is most suitable for this titration? Okay, give a reason for the answer by referring to the data in the table. So P, I'm expecting P to be suitable, okay? And why? We have a weak base and a strong acid, therefore your product should be acidic. Okay, and therefore you're expecting a range to be less, pH range to be less than 7. All right, now 7.2. So it says when 0,1 moles, 0,01 moles of dilute sulfuric acid is mixed with 0,024 moles of potassium hydroxide. So now you have a strong acid and a strong base, but that acid is diluted. So yeah, what does that do to its strength? Okay, potassium hydroxide, the total volume of the final solution, so V total, is equal to 0,2 cubic decimeters. And we have that reaction there, okay? Chemical formula that has been given. Now, 7.2.1, they ask us there, what is meant by dilute acid? Okay, so a dilute acid, it's a solution of an acid in water, and it has a low concentration of the acid molecules. Okay, that is what, if you dilute something like you dilute juice, it's going to be less sweet. Okay, so basically this solution has a high amount of water and a low amount of acid. And the last question for 8 marks, calculate the pH of the solution. Okay, 8 marks, we're going to do some work here. All right, so initially, okay, let's look at initial conditions. Sorry about that. So we have our sulfuric acid, which is 0,01 moles, okay, and then it's mixed with 0,024 potassium hydroxide. So this is the initial amount of, these are initial amounts, by the way. I'm just going to put I's there to say this is the initial amount, which is 0,024, and then the total volume of the final solution is 0,2 cubic decimeters. Okay, so where are we going to start? 7,2,2, we are going to look at the ratio, okay, according to the formula. So when it comes to potassium hydroxide, there we have 2 moles. And if we look at our sulfuric acid, we have 1 mole. Okay. So what are we going to use up here? If we have our initial mole for potassium hydroxide, what will be the number of moles that are used up in this reaction? Okay, so the number of moles for potassium hydroxide that will be used up, if I have 1 mole of sulfuric acid, which is now 0,01, then it means I need to have twice for potassium hydroxide. Okay, let's put it like this, mole. Okay, so now if I deal now with the excess number of moles, I need to look at what I had initially and what I have now used up for potassium hydroxide, because that's the more, I have more information for potassium hydroxide. So in excess, initially I had 0,024, and what I used up is 0,02. So in excess, then I have 0,004 mole. And then I can use that excess to then get the concentration of potassium hydroxide. Okay, remember, because this is a very strong base, it dissociates completely, and we'll see how that comes into play. So we have now concentration is number of moles over volume. So number of moles, we have 0,04. The volume they told us is 0,2. Okay, let me just get the calculator before I miss the zeros. 0.04 divided by 0,2. So I get 0,02 mole. That's the concentration of potassium hydroxide. Now, the concentration of potassium hydroxide is really just equal to the concentration of the hydroxide. Okay, that's why I said because it dissociates completely. Okay, and we have, 1 mole of potassium, not 1 mole. The charge there is just positive and there we have negative. So it's fine. We can then conclude that the concentrations are the same. Okay, if I had something different, I don't know what to use, but if maybe I had an atom that needed twice, or maybe, okay, let's say calcium hydroxide, I will need twice of the hydroxide, so it will not be just equal like that. I would have to factor the 2 in here. All right, anyway, back here, so we have 0.02 moles per cubic decimeters. And now we can use our, because now we're dealing with the base, we're going to use our pOH formula. Remember, pH is equal to log, and then the hydronium, concentration of the hydronium. Okay, in that same sentence, we can say pOH, the negative log, I forgot there, let's just make sure. In that same attitude, we can also use pOH, which is negative log, and instead of H3O for the pH, we can actually use OH for the pOH. And the nice thing is that pH plus pOH is actually equal to 14. Okay, and if we want pH, it's basically going to be 14 minus pOH. But let's go and calculate what the pOH is. So if negative log of that concentration, which is 0.02. And if we check on the calculator, negative log 0.02, that's then equal to 1.69. Okay, no, that's going to be 1.70. Okay, no unit. So if we want the pH, it's going to be 14 minus 1.7. So it's going to say 14 minus the answer, and then we get 12.3. So it's quite basic, and that makes sense that it will be basic. Why? The acid, even though it was a strong acid, the acid was diluted. It means there was a high amount of water as opposed to the acid. Okay, so it diluted it, and we have a very strong base, so we're expecting the pH then to be quite basic. Okay, if it wasn't diluted, we just had sulfuric acid as it is and potassium hydroxide as it is, our pH would be closer to 7. But yeah, that's it for question 7. All right, second last question, question 8. The relationship between the concentration of the electrolyte and the cell potential is investigated using the following electrochemical cell represented by the cell notation. Okay, so we have aluminium, and we can see, so if we have our cells there, yes, girl, yes. So she wants to teach you guys today. But anyway, so we can see that aluminium is the anode. Okay, so we would have the aluminium in here, and at the anode, that's where oxidation occurs. Okay, so that is what happens. And then we have this metal. Okay, so we don't know what it is. It's M. I almost said it's magnesium, but it's just M. Okay, so we have M this side. It is being reduced. Okay, so that is at the cathode. That's where the cathode is. All right, so the concentration of M2 plus is changed and the corresponding EMF is measured. The concentration of aluminium and the temperature are at standard conditions. Okay, if they say standard conditions, we know our temperature is around 25 degrees Celsius. Our concentration, we have 1 mole per cubic decimeters. The graph below shows the results of this investigation. Okay, so we can see on the y-axis is the EMF, x-axis is the concentration. So it says here, identify the reducing agent in the cell. So reducing agent, that's where oxidation occurs. So in this case, that would be aluminium. And then it says, determine the concentration of M2 plus that will produce an EMF of 1,87. Okay, so if we have a look here, 1,87, let me just try to indicate that. So yeah, we can highlight that and see what is what. Yes, so 1,87 is here. Okay, and at this point, this is where we are. Oh no. This is where we are. All right, so if I take these little spaces over here, I can see that it's actually 0,025. Okay, 0,025, because the space in between here is 0,25. Okay, so if I want to know what the reading is, it will be 0,25 plus the 0,025. And how many blocks do we have there to get to our answer? 3 blocks. So basically, we have 0,25 plus 0,025 times 3. So answer 0,325 volts. Okay, did you answer the question? Just make sure, determine the concentration. Oh my word. This is not volts, this is concentration. Mole per cubic decimeters. Okay, so we got it. And then the next question, 8.3. How will the concentration of M2 plus ions be affected as the cell operates? Okay, remember in here, this is our cell where, okay, these are electrodes. Okay, I'm drawing this incorrectly, but the electrons flow in that direction. Okay, electrons flow in that direction. This is negative, this is, no, that's positive, that's negative. So electrons flow in this direction. All right, and here we're going to have positive ions. And this side, the electrons are flowing. You find some positive ions, and then you create this metal M. So this M2 plus ions, the electrons are coming to neutralize them. Okay, so now it says, how will the concentration of M2 plus ions be affected as the cell operates? Choose from increasing, decreasing, or remain the same. So because the electrons are coming, like, okay, each 2 electrons are coming, they're like, we want that M2 plus, okay, so that we can form M. All right, so these ones will keep decreasing. Okay, so yeah, basically if I were to write this down, I would say that the M2 plus ions are reduced, okay, by the gain of electrons, okay, to form M, okay, the metal M. All right, so now 8.4. Potassium nitrate is used in the salt bridge of the cell. Okay, there we go. We have potassium nitrate. I hope you know that the charge of potassium is positive and that of the nitrate is negative. Okay, this is a big O as well. Okay, now what does it say? To which electrode will the K plus ions move in the salt bridge? Aluminium or this metal M? Okay, so remember, aluminium is busy releasing electrons, so it's becoming positively charged. So these two are actually going to repel one another. Okay, but what's happening then with M? M is being neutralized. Okay, it's being reduced, sorry. So where will the K ions go? They'll definitely go to M. Alrighty. Sorry guys, I'm trying to move as fast as I can. It's not easy recording with the baby. And yeah, church is about to start as well. Okay, 8.5. Identify metal M with the aid of a calculation. Okay, so in this case, we're going to go to our E cell. Okay, because we have standard conditions, so we know that cathode-ish, apparently must write this all down. You can't just say E, cath, and then anode. So we know what's at the anode. The anode, we said, is aluminium. Okay, while we're here, let's go to our table of standard reduction potentials, and let's then go and see what is there at the anode. So where is aluminium? At the top, at the bottom? I'm just looking for it now. Oh gosh. Okay, let's start from oh, there is aluminium. Okay, so it's negative 1,66. Okay, so this is what we're looking for at the cathode. Okay, minus 1,66. Okay, and then what about at the cell? What do we have there? Okay, so E cell, what we are expecting is, because we have standard conditions, we know that our concentration is 1, right? Okay, so with a concentration of 1, we can go and then just look at the graph again. I shouldn't have removed that. But yes, look at the graph. What's happening there at 1? What would be our potential? What would the V value be? If I lost the EMF value, what would it be? Okay, so we have 1. It goes all the way there. And, oh, there we go. It's 2. I actually didn't need to show this, but it's fine. So we have 2 here. So now the reading at the cathode for metal M is going to be 2. So minus will give you a plus, but if you take it to the other side, it's going to be minus again. Okay, so 2 minus 1,66, that's going to be 0,34 volts. That sounds very familiar. Okay, let's see. So we're going to look for 0,34. And there we have it. It is copper. Okay, so M is actually copper. Or you would have just said Cu. Okay. Geez, how many marks was that? I think I saw a lot of marks. But anyway, I'm rushing through it. 6 marks. That's a nice 6 marks. So that is metal M. Okay, and then 8.6. Metal M is now replaced with magnesium. Okay, so we have M, which is copper. I'm just going to say copper. And now we're replacing it with magnesium. Which electrode, aluminium or magnesium, will be the anode? So between aluminium or magnesium, which one will be the anode? Okay, let's check which one is more likely to oxidize better. So aluminium, I lost it again. Where was it? Okay, magnesium, I see. There it is. Oh, they're actually next to each other. Okay, so between magnesium and aluminium, so magnesium is above aluminium. All right, so it has what? Negative 2,36, and aluminium, like we know, negative 1,66. Okay, let's just go back to the question. Okay, so yeah, which electrode, aluminium or magnesium, will be the anode? Remember, at the anode, that is where oxidation occurs. Okay, anode, that's where oxidation occurs. That's where it's more likely to release its electrons. And if we look at, I shouldn't actually have left that table. If we have a look at our description, so as we go up, it's increasing strength of reducing agents. So as you go up, Reducing agent meaning it can oxidize way better. And magnesium is on top of aluminium. So magnesium can actually oxidize way better. Okay, I hope I'm making sense. For 8.6.1, which one will be the anode? Magnesium, more than aluminium. Okay, because it wants to oxidize much better, because as you go up, the increasing strength of you have the increasing strength of reducing agents. So increasing strength in the ability to oxidize, basically. Okay, and then we can say what? So which electrode will be the anode? Magnesium. And then 8.6.2, refer to the relative strengths of the oxidizing agents to explain the answer. So like I said, so magnesium, actually, negative 2.36, whereas you have aluminium, which is negative 1.66 volts. Okay, so magnesium, being the anode, it oxidizes better. It has a its strength, or its ability to oxidize. Yes, its ability to oxidize is much better. It's much stronger. Okay, so yeah, it's the, yeah, I don't know how to say it much better in nice English, but yes, the strength of its oxidizing, or it being able to oxidize effectively, is way better than aluminium. You'll put it in nice words. I need to rush. We're done with question 8. All right, let's go to the last question, question 9. The simplified diagram below represents the cell used for electroplating ornaments with silver. P and Q are the two terminals of the battery. Okay, so when I see the ornament, I know that's the thing that needs to be plated. So for me, that makes sense for it to be the cathode. Okay, so this is the cathode in here at P, and then Q, that would be the anode. So that's the cathode, that's the anode. Okay, that's what I'm focusing on, that's what I'm looking at. All right, now it says state the energy conversion that takes place in this cell. Okay, so in the cell, which is electrolysis, okay, we're then going from electrical energy all the way to chemical energy. Okay, let's do that. Okay, so 9.1, like I said, we're going from electrical energy all the way to chemical energy. We need a battery, we need its power in order to, do something there. And then 9.2, which terminal of the battery, P or Q, is negative? Okay, what did we say? At the anode, okay, positive. At the cathode, negative. So which terminal of the battery is negative? P. Okay, that's where reduction occurs. And then it says, write down the equation of the half cell reaction taking place at the cathode. Okay, so basically we are trying to get the solid silver. Okay, so let's just go to the table. We'll be looking for silver, the cathode. Geez, why isn't it popping out for me? Yeah, guys, my kid likes to sleep. Okay, so because it's at the cathode, we're going to write it as it is. So we're going to have Ag plus, and then we have 1 electron. And there we go. Okay, that is the equation that we have there. All right. That's the equation of the half cell. And you must be careful to put only 1 arrow. Don't put 2 arrows or else it's wrong. Okay, and then it says calculate the current that is required. The current required to electroplate the ornament with that mass of 3.25 grams of silver in 30 minutes. 30 minutes. So times 60, and we're gonna get the seconds there. Okay, So now let's try firstly to work out the number of moles for silver. Okay, so we have the mass over the molar mass. Okay, they gave us the mass, it's 3,25. And then what is the molar mass of silver? Ag, hope you can see that's 108. All right, and now we're going to take out our calculator. So the mass is 3,25 divided by 108, and we get 0,03 mole. Okay, now what then are we going to do? We need the current. Okay, so in order for us to get current, let's just remind ourselves what we're working towards. Charge over time, right? That's pretty much what current is. So now we have the number of moles for this silver, okay? And because we're going to deal with charge and all, we need the number of moles for the electrons as well. Okay, so the number of moles then for electron will be equal to, because for silver we need 1 electron. Did you see? Okay, so 1 mole, 1 is to 1 basically, so 0,03 mole for the number of mole of the electron. And then what we're going to do, we want to find charge, right? And in order to do that, we're going to use Avogadro's number in order for us to get the amount of molecules or atoms that we have. Okay, so we're going to use our equation over here, where N is equal to N over Na. Okay, so we have there our number of moles, which is 0,03. We are looking for N, and then Avogadro's number or constant is 6,02 times 10 to the 23 per mole. So we're basically here looking for N. Okay, let's calculate that. So we have 0,03. That's our answer, multiplied by 6,02 times 10 to the power 23. And we have 1,81, okay, times 10 to the 22. Sorry about that, guys. The snoring and everything, it is what it is. Okay, now we can get to our equation. I is equal to Q over delta T, actually, not just T. So, we're almost there. Q over delta T. So we have our charge there. Do we have it as yet? So this is the number of electrons. And then what are we going to do now to get our Q? Because we're not there yet. So Q is equal to that in there times the charge of an electron. Okay, so we have 1,81 times 10 to the power 22, and we're going to multiply it by charge of an electron because we want charge at the end of the day. Okay, and then what do we get? So multiplied by 1,6 times 10 to the power negative 19. Okay, we get a value there of 2898,52 coulomb. Ooh, okay, coulomb. Now we can use that. 2898,52. 52. I'm rushing, guys. I have a meeting and I'm so late. Okay. The time we said it is 30 times 60. Okay. Yeah, what an ending to this paper. Snoring and rushing, but you get it, right? So yes, here we go. We have 1,61 amperes. That is the current. We are done with the paper. Am I done? Did I answer? Calculate the current? Yes, we did. 5 marks. Thank you, guys. All the best for tomorrow's test. Cool.